In lesson 3 today, we're going to look back at solving equations. You have an equation when you have a statement that two expressions are equal to each other. We call that an equation. And we have a solution to the equation when we know all the values of the variable that make the equation true. And when you want to undo operations, those are called inverse operations, which is the easy method for solving equations. We're just going to do the opposite of what's being done. And when an equation is true for every value of the variable, that's known as an identity. And we have a literal equation when you use at least two different letters as variables. Some ideas of literal equations are like the area for a circle or the perimeter formula, all of those types of things, slope-intercept form, stuff like that. So here are the properties of equality, and A, B, and C are representing real numbers. So the reflexive property says a number is equal to itself, like 4 is equal to 4. And something is symmetric if we say if x is equal to 3, then you can rewrite that as 3 is equal to x, and you've kept the equality. The transitive property says, let's say, if 4 plus 3 is 7, and w is equal to 7, then we could say that 4 plus 3 is equal to w, using the transitive property. And then for substitution, if we know x equals y, and we know 5 plus x equals 9, then we can say 5 plus y equals 9, using the substitution property. In example 1, we're going to solve one-step equations using inverse operations. In the first example, we have x plus 9. So I want to look at what's happening to x. We are adding 9. So to do the opposite of add 9, we would subtract 9 from the left and from the right. I'm using inverse operations, so the opposite of add 9 is subtract 9 on the other side, if you think of it that way. Negative 15 minus 9 is negative 24, and to just mentally check, negative 24 plus 9 is equal to negative 15. In 1b, 12 is multiplying on our variable b. So to undo multiplication, we want to divide by 12. And 12 doesn't go into 18 evenly, but we know we can simplify that. Since 6 goes into both 12 and 18, then our variable b, 6 divides 12 2 times, and 6 divides 18 3 times. So our variable b is 3 over 2, or 1.5. When we have two-step equations, we have to do two different inverse operations. In this case, we have negative 3 times y plus 7 and 4/10. So what's happening to y first is we're adding 7 and 4/10. The inverse operation of adding is subtracting. So we want to subtract 7 and 4/10 from both sides. 20 and 9/10 minus 7 and 4/10 is 13.5. Now looking back over to the left-hand side, y is getting multiplied by negative 3. So the opposite of multiply would be to divide by negative 3. And negative 3 divides 13.5, negative 4.5 times. I'll leave the checking up to you. In 2b, do you know what to do first? We have 2/3 times y minus 7. So the furthest thing away from the y on the left left-hand side, I just want to look over here. The farthest thing away is -7. And the opposite of subtract 7 is to add 7 to the 5. So 7 plus 5 is 12. So we want to do the inverse operation. And then we see on the left-hand side, we're multiplying by 2/3. So you can think of it as dividing by 2/3, or division is multiplying by the reciprocal. So we're going to multiply by 3/2. So when you do that operation, that inverse operation, to get rid of the 2/3 on the left, we have to do the same thing over here to the right. Multiply by the reciprocal. 2 divides 12 6 times, and 6 times 3 is 18. So y is 18 is our solution. When we have grouping symbols, there's sometimes a variety of ways. In this first one on 3A, my approach is going to be to divide 4 into 56 instead of using distributive property. You can go do the approach either way, but I'm seeing 4 divides 56 evenly, and it goes into 56 14 times. Then 3m plus 5, we want to get rid of adding 5, so we'll subtract 5. 14 minus 5 is 9. And 3 times m, we want to do the opposite, so multiplying the inverse would be division, and 9 divided by 3 is 3. And then in example B, we do need to use distributive property so that we can collect like terms. I see 14y minus 35, and then minus 8y equals 1. So to get the y's together, we could add 35 to the right side and then collect like terms. 14y minus 8y gives us 6y, and 1 plus 35 is 36. Finally, we want to undo multiplying 6 on the y, so dividing 6 on both sides. 6 divides 36 evenly, and y equals 6. And then lastly, you could either multiply both sides by 3, but I see 1/3 of 9 and 1/3 of 15 is relatively pretty straightforward. So using distributive property, we could get 3 divides 9 3 times, and 1/3 of 15 is 5. Using inverse operations by subtracting 5, -7 minus 5 is -12, and dividing both sides by 3, our solution is -4. In example 4, we have a few more difficult equations. Let's take a look at those. Using distributive property, -6k minus 15 equals -9k minus 36. I want to add 9k to the -6k, and I want to add 15 to the -36. So we got the k's on the left and the constants on the right. 3k equals -21, and 3 divides -21 -7 times. On 4b, we're going to use distributive property 2 times. In the first case, it's 6x minus 3. In the second case, we've got -2 times 3 and -2 times +4. And then I want to collect all the x terms. But if you notice on the left side, 6x subtract 6x, that's 0. And -3 minus 8 is -11. And here's where we can use that property, the symmetric property. If you like to keep the variable on the left, using the symmetric property, we could just rewrite that and divide both sides by 11. Then x is going to be -1. In this last example, in example number 4, there's 2 approaches you could take. One approach is the idea that cross products are equal. You know, it's the way we check fraction reduction or simplifying. Let's say 10 over 2 is equal to 5 over 1. And in elementary school, you might have learned that the product of the means is equal to the product of the extremes. And that's the way we checked that our fraction simplification was equal. And a lot of times you'll call that cross multiplying. So that's the rationale for how we're going to do this. I'm going to say that it's the property of cross products are equal. So if cross products are equal, you can multiply the numerator on the left by the denominator on the right. So 8, this 8 times the entire numerator. That's 8 times the quantity 2x minus 5. And then the 4 on the denominator times the -3 on the numerator. So -3 times 4. 16x minus 40 is equal to -12. And 16x is equal to 40 minus 12, so that's 28. And x is 28 over 16, and we can simplify that to 7 over 4. Now, that's fine to do that, and many people will choose that way, but I also noticed something. I noticed that 4 and 8 are evenly divisible by 4, or 8 is a factor. 4 times 2 is a multiple for 8. So I want to think about that as clearing the denominator. And when you think about it from that approach, if I wanted to clear the denominator first, I could multiply the left side fraction. I could multiply that fraction by 8, and I could also multiply the right side fraction by 8. It would completely clear that denominator on the right, and 4 divides 8 evenly 2 times because 4 times 2 is 8. So that leaves us distributive property. 2 times 2x and 2 times -5, and then -3, and you see 4x is 7, so x is 7 over 4. We get the same result, just with a different approach. So whether you think about it as cross products being equal or clearing the denominator, either approach works. In example 5, we've got a formal garden can incorporate hundreds of thousands of brightly colored flowers, as well as grass, gravel, and fountains to form designs. Suppose we have a garden whose perimeter is 320 meters. What would the dimensions of the garden be if the length is 3 times the width? So first we need to have the formula for perimeter of a rectangle. That would be 2 lengths plus 2 widths. And here we see the perimeter is told to us as being 320 meters. And we're also told that the length is 3 times the width. So we can name length. Here's a sentence. L equals 3W. So we're going to write that. L equals 3W. And then we're going to take these 3 pieces of information, and we know perimeter is 320, So 2 side lengths and 2 width pieces has to be 320. But we know the length is 3 times the width, so we're going to substitute 3W in place of the letter or the variable L, and then add 2W, and that's going to equal 320. So 6W, this is 6W and 2W, that's 8W, is 320. So W must be 40, and the units were in meters. So the width of the garden is 40 meters. And if the length is 3W, then 3 times 40 gives us the length of 120. So we know that the garden is going to measure 40 meters wide by 120 meters long. So we know the measurement of the garden. And then 2 more to go. In example 6, we're going to solve standard form for a line. We're going to isolate y in this literal equation. So to get y alone, we want to subtract a times x from both sides. And to get y alone, we're going to divide every term by b. So y is negative a divided by b with the x plus c divided by b. And I see this as an mx plus b situation. So that tells me if I wanted to know b, I would do c over b, and if I wanted to know the slope, I would use the opposite of the a value divided by b. So in slope-intercept form, mx plus b, you can see substitutions there. And then the equation for Kelvin is a temperature scale. If Kelvin is Celsius plus 273 degrees, then we could say Celsius is Kelvin minus 273 degrees. And then in our last example, collecting like terms, 7 minus 4 is 3x plus 6, and 12 minus 8 is 4 plus 3x. If we subtract 3x from both sides, we get a false statement. 6 is not equal to 4, and this is never true. So this is a never true statement. In the last example for B, using distributive property, 3 times x and 3 times negative 4 and 2 times 2x and 2 times negative 6. Collecting like terms, we have 5x minus 12 on the left. We have 5x minus 12 on the right. This is a true statement. So this is something that's called an identity. It will always be true for any real number you substitute for x. And that, my friends, finishes lesson 3.